They need broad knowledge across various fields, and they need to work well as a team under extreme stress. Finding people with all these qualities is hard. Training them is expensive and time-consuming, and even then, there are no guarantees. Now, let me talk about the psychology of Mars missions. I mentioned this in part 1, but let me go deeper. The psychological challenges may be the hardest to solve. We study isolation and confinement extensively. Antarctic research stations, submarine crews, isolation chambers, and we learn that even the best people have limits. Common problems include depression, anxiety, interpersonal conflicts, performance degradation, sleep disorders, and in extreme cases, psychological collapse. On the International Space Station, ISS, these problems are manageable. Missions are generally 6 months long. The crew can see Earth. They can communicate with family and friends. They know rescue is possible if something goes very wrong. On Mars, none of that applies. The mission is 900 days long. Earth is just a star in the sky. Communication has delays of minutes to tens of minutes. There is no rescue option. The psychological pressure would be immense, and we cannot fully simulate it on Earth. We cannot replicate the real danger, the real isolation, the real awareness that you are alone. Some people will handle it well, but others perhaps won't. And if someone has a severe psychological problem en route to Mars, there's no psychiatric hospital. The crew has to manage on their own. In extreme cases, other chemical interventions might have to be considered, medication to control anxiety, depression, and psychosis. But medications have side effects. They can impair judgment and performance, and the supply is limited. You can't bring unlimited quantities. There's also the issue of crew dynamics. Put 5 or 6 people in a confined space for 900 days, and conflicts are inevitable. Personalities clash. Resentments build up. Small annoyances turn into major grievances. On Earth, you can separate people who don't get along. On a Mars spacecraft, you're stuck together. You can't separate. We try to select crews with compatible personalities. We train them to work together. We teach conflict resolution skills. But there's only so much you can do. Human nature is human nature. And there's one more psychological factor that people don't often consider: the overview effect in reverse. When astronauts see Earth from space, they often report a profound sense of awe and connection to the cosmos. They see Earth as a fragile, beautiful, unified whole. But on the way to Mars, Earth shrinks to a point. You lose that connection. You are truly alone in the cosmos. Some people might find that liberating. Others might find it terrifying. We don't know how people will react. We can't know until we actually send them. Now, let me tell you something personal. When I teach physics to my students, I always emphasize the importance of understanding principles rather than memorizing facts, because facts change, but principles endure. The same applies to Mars exploration. We cannot memorize solutions for every possible problem. We need teams that understand the principles, who can think creatively, who can solve novel problems with limited resources. The Apollo 13 mission demonstrated this. When the explosion happened, the crew and mission control improvised solutions using duct tape, plastic bags, and whatever materials were on hand. They understood the principles of life support, orbital mechanics, and energy management, and that knowledge saved their lives. Mars crews will need that same ability to improvise, but they will be more autonomous. Mission control can advise, but with the communication delay, real-time help is impossible. So, we need not just technically skilled astronauts, but creative problem solvers, and those people are rare. Now, let me talk about cost. This is often overlooked in discussions about Mars exploration, but it's crucial. Mars missions will be expensive, very expensive. NASA estimates a crewed Mars mission could cost $500 billion or more, requiring 10 to 15 years of development and execution. $500 billion. That's more than the entire Apollo program adjusted for inflation. And that's probably optimistic. Large government programs almost always go over budget. The actual cost could be $700 billion, a trillion. Who knows? Where does this money come from? Government budgets are finite. NASA's current budget is about $25 billion a year. A Mars program would consume a large chunk of that for years or decades. That means other programs get cut. Scientific research, Earth observation, astrophysics. All of it competes for the same funding. Is Mars worth sacrificing those programs? Some people say yes. They argue that Mars is inspiring, that it advances human knowledge, that it ensures our survival as a species. All valid points. Others say no. They argue we should focus on problems on Earth, that robotic missions are more cost-effective, that the money could be better invested elsewhere. Also valid points. I'm torn. As a physicist, I believe in exploration and pushing boundaries. But as a practical person, I recognize that resources are limited and choices must be made. Private companies like SpaceX could change the equation if they can drastically reduce costs through reusability and efficiency. Mars could become more affordable. Elon Musk talks about costs in the tens of billions rather than hundreds of billions. But even tens of billions is a lot of money. And private companies need to justify the investment. What's the return? Tourism, mining, scientific data? None of these obviously generate enough revenue to justify the cost. So, we're left with a conundrum. Mars is expensive. The benefits are uncertain. The risks are high. Yet, we are planning to go. Why? The answer, I believe, is that it's not purely rational. It's partly emotional, partly about national prestige, partly about human ambition. We want to go to Mars because it's there, because it's the next frontier, because that's what explorers do. But emotion and ambition aren't enough. We need a realistic assessment of the challenges and an honest appraisal of our capabilities. Now, let me talk about mission architecture. How do we actually get humans to Mars and back? Several concepts have been proposed. The most common is the opposition class mission. You launch when Earth and Mars are on opposite sides of the Sun, use a fast trajectory to Mars. Stay on the surface for a short period, maybe 30 days. Then return on another fast trajectory. Total mission time is about 500 days. The advantage is the shorter duration, less radiation, less microgravity, less time for things to go wrong. The disadvantage is the higher energy requirements. You need more fuel for fast trajectories. Another approach is the conjunction class mission. Launch occurs when Earth and Mars are properly aligned. Use a slow, energy-efficient trajectory to Mars. Stay on the surface for about 500 days while waiting for the return window. Then return home on another slow trajectory. Total mission time, approximately 900 days. The advantage is the lower energy requirement. You need less fuel. The disadvantage is the much longer duration, much more radiation, and much more time isolated. Currently, NASA favors the conjunction class because it's more feasible with existing or near-term propulsion technology, but it also demands more of the crew. There's also the question of whether to send everything in a single launch or multiple launches. A single launch is simpler. Everything works together, but it requires a huge rocket, probably larger than any we've ever built. Multiple launches allow for the use of smaller rockets, but require orbital assembly. You launch the components separately and assemble them in Earth orbit, and then send the assembled spacecraft to Mars. This adds complexity and risk. And what if a launch fails? What if the assembly doesn't work? And there's the issue of prepositioning. Do you send cargo before the crew? Earth supplies, equipment, and even the return vehicle to Mars before the humans arrive? This reduces risk. The crew knows their supplies are waiting, but it requires multiple missions and assumes the cargo arrives safely. Every architecture has its pros and cons. Every choice involves trade-offs. There is no obviously superior solution. Now, let me talk about abort scenarios. What happens if something goes wrong on the way to the moon? Apollo crews could abort the mission and return home relatively quickly. On the way to Mars, there is no quick abort. If a problem occurs during the outbound journey, you cannot turn back. Orbital mechanics don't permit it. You are committed to continuing to Mars. Your only hope is to solve the problem or work around it. If a problem occurs on Mars, your options are limited. You could try to launch before the optimal return window, but that requires more fuel and you might not have it. If the return vehicle fails, you're stranded. There is no rescue mission coming. No one can get there in time. Your supplies slowly run out and you die. What a terrible situation. But it's the reality. Mars missions have very limited abort options. The crew needs to understand they are undertaking enormous risk. Now, some people argue that we should send one-way missions only. Send people to Mars with no intention of bringing them back home. They live out their lives on Mars. Establish a permanent settlement. This would be cheaper and easier than round-trip missions. You don't need a return vehicle. You don't need fuel for the return trip. You just need enough supplies to sustain life on Mars. But is that ethical? Are we asking people to voluntarily exile themselves on Mars, to never see Earth again, to die on a hostile world, far from home? Some people would volunteer. There's no shortage of people willing to go to Mars, even on a one-way trip. But does that make it right? I'm conflicted. On the one hand, people should have the freedom to make their own choices. If someone wants to go to Mars and stay there, who am I to stop them? To say no? On the other hand, there's something troubling about that idea. It feels like we're giving up on solving the hard problems. Instead of figuring out how to bring people home safely, we're just leaving them there. And one-way missions don't solve most of the problems. The crew is still exposed to radiation during the trip. They still need life support on Mars. They still need food, water, and power. The challenges are pretty much the same, except for the issue of the return vehicle. So, I'm skeptical about one-way missions. I think if we're going to send people to Mars, we should plan on bringing them back. Anything less than that feels like failure. Now, let me talk about timelines. When will humans actually go to Mars? SpaceX says it will be in the 2020s. NASA says it will be the 2030s or 2040s. Other estimates are even further out. My prediction is that it won't happen in the 2020s. The technology isn't ready yet. We haven't solved the radiation problem. We haven't built the spacecraft yet. We haven't tested the systems. Maybe by 2032, if everything goes well, if funding holds, if technology develops as expected, if we are willing to accept significant risks, it will probably be in the 2040s or 2050s. And even then, I'm not sure it will happen. Why am I pessimistic? Because the challenges are so immense. Because every solution creates new problems. Because we keep discovering things we didn't even know we didn't know. The more we study Mars, the harder it seems. 50 years ago, we thought Mars was relatively benign. Maybe it had a thin, cold, but survivable atmosphere. Now we know about the perchlorates, the dust storms, the radiation levels, the psychological challenges. It's worse than we thought. And history shows that ambitious space programs often fail. The space shuttle was supposed to fly weekly and cost $10 million per launch. It flew monthly, at best, and cost $500 million per launch. The ISS was supposed to cost $8 billion and be completed in the mid-90s. It cost over $100 billion and wasn't completed until 2011. Grand undertakings are almost always harder, slower, and more expensive than initially predicted. A Mars program will likely follow the same pattern. So when people ask me when we'll go to Mars, I say maybe mid-century, maybe later, maybe never, if we are honest about the challenges and decide it's not worth the cost and risk. And that brings me to the final question. We've established that Mars presents extraordinary challenges. Now, the next question is, and this is where things get really interesting, what are we actually doing to solve these problems? What technologies are under development? And, more importantly, are they enough? You see, when you look at the proposed solutions for Mars travel, they fall into two categories. First, there are incremental improvements, making chemical rockets more efficient, improving life support systems. Second, there are revolutionary technologies, like nuclear propulsion, artificial gravity, advanced habitats. The problem is that incremental improvements aren't enough, and the revolutionary technologies aren't ready yet. We're stuck in the middle. We're trying to get to Mars with tools that aren't quite good enough. Let me start with radiation shielding, because this is the most critical problem. Several solutions have been proposed. Some people say we should use water as shielding. Water is effective at blocking radiation, and you need water anyway for drinking and other purposes. So, you surround the crew compartment with water tanks. When you need water, you use it, and the shielding gradually diminishes. It sounds clever, doesn't it? But here's the problem. To ensure adequate protection, you need several meters of water all around. That's hundreds of tons of water. Even if you recycle most of it, even if you use it as propellant, the mass penalty is enormous. And water isn't perfect shielding. It blocks some radiation, but high-energy cosmic rays can still penetrate. You might reduce the dose, maybe by half, but the astronauts would still receive dangerous levels of radiation. Another proposal is to use the spacecraft's fuel as shielding. Liquid hydrogen, for example, is a good radiation shield. So, you design the tanks to encircle the crew compartment. As the fuel is burned, the shielding diminishes, but by then you're probably close to your destination. Again, clever, but again, insufficient. And it only works for part of the journey. Once on Mars, when the fuel is gone, you're unprotected. Some people propose using magnetic fields to deflect charged particles, creating a miniature magnetosphere around the spacecraft. This could work for solar particle events, which are charged particles from the sun. But cosmic rays are so energetic that even strong magnetic fields can't deflect them effectively. And generating a strong enough magnetic field requires enormous amounts of energy. Then there's the idea of simply accepting the radiation risk and developing medical countermeasures. Drugs that repair radiation damage, gene therapies that make cells more resistant. This is being researched, but we are still far from having effective countermeasures. And even if we develop them, there's a limit to how much damage the human body can repair. So, after analyzing all the proposed solutions, I have to be honest, we don't have a good answer to the radiation problem. We can reduce the dose. We can mitigate the risk, but we cannot eliminate it. All astronauts on Mars would have to accept a significant increase in cancer risk and neurological damage. That's the reality. Now, let me talk about artificial gravity. This would solve the microgravity problem. If we could create artificial gravity on the spacecraft so that the astronauts' bodies wouldn't deteriorate during the long journey. The principle is simple: rotation. If you spin a spacecraft, the centrifugal force creates the sensation of gravity. The faster you spin, or the larger the radius, the stronger the artificial gravity. Now, for maximum comfort, to create Earth-like artificial gravity, you need a large radius or a fast rotation. Ideally, you need both. A spacecraft with a radius of about 100 meters spinning once per minute to create Earth-like gravity. But here's the problem. Building a 200-meter diameter spacecraft is incredibly challenging. The structure would be enormous. The mass would be huge. The cost would be astronomical. SpaceX's Starship, the most advanced Mars spacecraft under development, is 9 meters in diameter. To create a rotating artificial gravity system with Starship, you would need to connect two spacecraft and spin them around a common center. The tether would need to be hundreds of meters long. And that creates new problems. The tether has mass and complexity. The dynamics of a rotating system tethered together are complex. Any movement of mass inside the spacecraft affects the rotation. Docking with a spinning spacecraft is extremely difficult. And if the tether breaks, the spacecraft fly apart. Some people propose a middle ground, creating partial gravity. Perhaps at the level of Mars gravity, at 0.38 g instead of full Earth gravity. This would require less rotation, a smaller radius. But we don't know if partial gravity is enough to prevent physiological deterioration. It might help, or it might not. We simply don't have the data. And here's another problem. Even if we build rotating spacecraft, the astronauts would still experience zero gravity during certain phases. During acceleration and deceleration, when the engines are firing, you can't safely spin the spacecraft. During Mars orbit insertion, during landing, during launch from Mars. All of these phases require the spacecraft not to be spinning. So, you would have to use artificial gravity for part of the journey, but not all of it. And we don't know if that's enough to make a significant difference. In summary, artificial gravity is theoretically possible, but in practice, very difficult. No one has ever built a rotating spacecraft for humans. We've never tested the concept beyond small-scale experiments. It's an unproven technology. Now, let me talk about propulsion. Chemical rockets are too slow and inefficient for Mars. The journey takes too long. The fuel requirements are too high. We need better propulsion. Nuclear thermal rockets are one option. These use a nuclear reactor to heat hydrogen propellant to extremely high temperatures and then expel that propellant to generate thrust. They are about twice as efficient as chemical rockets. That's a huge improvement. With nuclear thermal propulsion, you could reduce the travel time to Mars from 9 months to perhaps 4 or 5 months. That means less radiation exposure, less microgravity exposure, less time for things to go wrong, and less fuel needed, which means less mass, which means a smaller rocket. So why aren't we using nuclear thermal rockets? Politics and technology. The technology exists. We developed and tested nuclear rocket engines in the 1960s and 70s. They worked, but the program was canceled due to political concerns about launching nuclear material into space. And there are legitimate concerns. If a nuclear rocket explodes during launch, you could scatter radioactive material over a wide area. The health and environmental consequences could be severe. The public doesn't like that risk. So, nuclear thermal rockets, despite their advantages, are politically problematic. NASA is researching them again, but it will take years before they are ready for real missions, if ever. Another option is electric propulsion, ion thrusters, Hall effect thrusters, and other types. These are extremely efficient. They can be 10 times more efficient than chemical rockets, but they produce very little thrust. An ion thruster might produce less thrust than the weight of a piece of paper on Earth. That means long acceleration times. You can't use ion engines to take off from a planet. They don't have enough thrust. But for deep space travel, they are great. You can run them continuously for months or years, gradually increasing speed. The problem is time. A mission to Mars using ion propulsion might take longer than one using chemical rockets. You accelerate slowly, coast, then decelerate slowly. The total travel time could be similar to or even longer. And a longer travel time means more radiation, more microgravity, more problems. So, electric propulsion doesn't solve our problems for Mars. It's great for cargo missions, for uncrewed probes, but for crewed missions, it's not ideal. Some people talk about more exotic propulsion, nuclear pulse propulsion, using nuclear explosions to propel the spacecraft, fusion rockets using the power of nuclear fusion, antimatter propulsion through the annihilation of matter and antimatter. These technologies would be revolutionary. They could reduce the travel time to Mars to weeks instead of months. But all of this is far in the future. We don't have working prototypes. We don't have the engineering knowledge required to build them yet. Decades away, perhaps centuries. So, in the near future, we'll be stuck with chemical rockets and maybe nuclear thermal rockets if we can overcome the political hurdles. And that means month-long journeys with all the associated problems. Now, let me talk about in situ resource utilization. The idea is that instead of bringing everything from Earth, you use Martian resources to produce what you need: water, oxygen, and fuel, and you have to extract them from the Martian environment. This is actually one of the most promising concepts. Mars has water ice and a carbon dioxide atmosphere. From that, you can produce oxygen, water, and even rocket fuel. The chemistry involved is quite complex. SpaceX is betting heavily on this. Their plan is to use the Sabatier reaction to convert Martian CO2 and hydrogen into methane and water. The methane becomes rocket fuel for the return trip. The water provides drinking water and oxygen. If this works, it drastically reduces what you need to bring from Earth. You only need to bring hydrogen, everything else you produce on Mars. That represents a huge mass savings. But here's the challenge. You need industrial equipment on Mars. Chemical plants, electrolyzers, pumps, storage tanks, power systems. All of this needs to work reliably in the hostile Martian environment for months or years. And you need power, a lot of power. Solar power is an option, but dust storms can block the sun for months. You need nuclear power, a small nuclear reactor that can operate on Mars. NASA is developing these devices, but they aren't ready yet. And there's another problem. You need to send this equipment to Mars before the crew arrives. You need to set it up robotically. It needs to work without human intervention because the crew needs to have fuel and oxygen ready when they arrive. If the system fails, the crew can't come home. So, in situ resource utilization is promising, but it's unproven. We've never done it. We've never operated chemical plants on another planet. It's a huge technological challenge. Now, let me talk about the entry, descent, and landing problem. This is one of the biggest engineering challenges in Mars exploration. Landing large masses on Mars is something we simply haven't figured out yet. The problem is the atmosphere. It's too thin for parachutes alone, but too dense to be ignored. When you enter the Martian atmosphere at high speed, you encounter tremendous heating. You need a heat shield, but the thin atmosphere doesn't slow you down enough. You need rockets to finalize the descent. For small payloads, like rovers, we use a combination: heat shield, parachutes, and then rockets for the final descent. For Curiosity, we used a sky crane, a hovering platform that lowered the rover on cables. It worked, but it was incredibly complex and risky. Now, at the scale of a human mission, you're not landing a ton. You're landing 20, 30, maybe 40 tons. The heat shield needs to be huge. The parachutes need to be huge. The rockets need to be powerful enough to slow all that mass down. And you need to do all of this with precision. You need to land close to your prepositioned supplies. You can't miss by hundreds of miles. You need pinpoint accuracy. SpaceX's approach is propulsive landing only. No parachutes, just rockets. The Starship would enter the atmosphere belly first, using its body as a heat shield. Then it would flip vertical and land on its engines, just like the Falcon 9's boosters do on Earth. It's an elegant solution in theory, but it hasn't been proven on Mars. Landing a 100-ton spacecraft on Mars using only rockets requires precise control, reliable engines, and a lot of fuel. If anything goes wrong, the spacecraft crashes. And here's another problem. The engines need to throttle down in the Martian atmosphere, reducing thrust to very low levels for a soft landing. And they need to do this reliably after months in space and a fiery atmospheric re-entry. That's incredibly challenging. Developing an engine takes years. Testing takes years. And you can't fully test a Mars landing on Earth. The atmosphere is different. The gravity is different. So, the entry, descent, and landing problem remains largely unsolved for human-scale missions. We have concepts, we have plans, but we don't have proven systems. Now, let me talk about life support. Keeping humans alive for 900 days in space and on Mars is an enormous challenge. We need systems that are reliable, efficient, and easily maintainable. The ISS has taught us a lot about life support. We know how to recycle water. The ISS recovers about 93% of water from humidity, urine, and other sources. We know how to generate oxygen from water through electrolysis. We know how to remove CO2 from the air. But the ISS is resupplied regularly. Cargo ships bring spare parts, new filters, equipment. If something breaks, a new one arrives in a few months. On Mars, there are no resupply missions. Everything needs to work for the entire mission duration, or you need to bring enough spare parts to fix anything that breaks. And things break. Murphy's Law applies in space. If something can go wrong, it will. Systems fail. Parts wear out. Unexpected problems arise. So, you need redundancy. Backup systems for everything essential. Multiple water recyclers, multiple oxygen generators, multiple CO2 scrubbers. But every backup system adds mass, and mass is the enemy. There's a trade-off. Too little redundancy, and a single failure could kill the crew. Too much redundancy, and the spacecraft becomes too heavy to launch. And some things are hard to make redundant. Can you have a backup habitat, a backup spacecraft? If the main systems fail catastrophically, what do? The answer is, you probably die. That's the harsh reality. Mars missions operate under extreme caution. Everything has to work, or the crew doesn't survive. Now let me talk about something frequently overlooked: maintenance and repair. On Earth, when something breaks, you call a technician. On the ISS, if something breaks and the crew can't fix it, they contact mission control and troubleshoot together, or they wait for a spare part on the next cargo ship. On Mars, the crew is the repair team. They have to fix everything themselves. They need tools, spare parts, and technical expertise. They need to be engineers, mechanics, electricians, plumbers, computer technicians, a bit of everything.